All right, guys, I know I said in the last one we were going to do Ox LDL. I found another paper that I couldn't resist because in a snapshot, this paper totally explains all of the stuff that I'm always talking about with the desaturase enzymes and the delta 6 desaturase and the delta 9 desaturase. So it's just a very interesting paper that we can't miss. But the good news is that will set up the context to talk about Ox LDL next week. So we're still going to do that. Let's get straight into this. I want to talk about dietary linoleic acid and its effects on heart disease as opposed to linoleic acid that you see in your body tissues, specifically in your phospholipid membranes. The paper we're going to get to, they looked in skeletal muscle phospholipids, which are the phospholipids are just the ones that make up the membranes on the outside of your cell. This is a different study, but they're looking at the relationship between dietary fats and your red blood cell membrane fats. And what they show is that, so palmitic acid, so these numbers here are the correlation scores. And the ones on the stars mean they have a statistically significant correlation. And these are different fats over here. So you can see 17O is a fat that's found in dairy. And you can see that has a correlation of 0.32, which is like a pretty good correlation. It's not like a massively strong correlation. If this number was 1.0, it would mean like if you ate all linoleic acid, then your membranes would be pure linoleic acid. That would be 1.0. And then as they go down and down, they're less strongly correlated. So 0.3 is like, that's a pretty good correlation. I mean, I think that's the strongest correlation that there is, but even something like 17O, which is a pretty good marker of dietary dairy intake, it's not a perfect correlation, right? It's good. Anyway, palmitic acid, there's literally no correlation at all. 0.008, that's nothing. So there's no relationship between how much palmitic acid, which is a 16 carbon saturated fat, that you eat, and how much is in your cell membranes. And we're going to get to why that is. The same with oleic acid. The correlation is 0.02. That's not correlated at all. Linoleic acid is somewhat correlated, 0.21. That's not bad, but it's not nearly as strong as something like 17O, which is a very good dietary indicator of intake. And so linoleic acid is kind of in the middle. And this one we're going to get to too, arachidonic acid 24N6 is a 0.06. That is not very well correlated at all between the amount that you eat and the amount that is found in your membranes. So this is a study of women who were pregnant, and some of them remain normal glucose tolerant, and some of them developed gestational diabetes mellitus. And the reason I'm showing this slide is that what you can see is there's really no difference at all in the diets between these two groups. And the reason that I show that is because most Americans eat more or less the same thing. So if you took 10 people and you gave them the exact same diet, and then 3 of them got sick and 7 of them didn't, you could say that the reason that the 3 of them got sick was probably because of their genetics, right? Because everyone is eating literally the exact same diet. And that doesn't mean that if you gave them a better diet, maybe the 3 people wouldn't have gotten sick. It just means that in the context of the standard American diet, the people who get sick, there is a strong genetic component to it. This is an example of that. This is SCD1. This is the first desaturase gene. And what you can see is that if you have this, this is just one gene, and you can either have the A version or the C version. And the people who have the C version are fairly well protected against developing, you can see this is coronary artery disease. So if you have the CC version of the SCD1, you are reasonably well protected against heart disease genetically. And this is another example in humans. This is in the D6D gene. That's the other desaturase, or one of the other desaturases. And you can see that if you have TT, if that's your genetics, you are more likely to be in the control group, which is to say you don't have heart disease. If you have the GG version, you're much more likely to have coronary artery disease. And so there's a lot of evidence that these enzymes are involved in the causal chain of these diseases like coronary artery disease. So this is the paper that got me excited about this talk. And so remember that I said that palmitic, right in the beginning, we said palmitic acid and oleic acid are not well correlated with your diet. And you can see here, these are healthy controls, and palmitic acid is at 16.6. These are people with coronary artery disease. Palmitic acid goes up to 19.9, and oleic acid goes from 9.6 up to 12.5. And so with coronary artery disease, palmitic acid and oleic acid both increase. And you can see I have DNL written there. And the reason for this is that de novo lipogenesis, which is when we make our own fat, de novo meaning new, lipogenesis meaning fat making. When we make fat, we take acetyl-CoA and NADPH, and fatty acid synthase makes palmitic acid. So if you're doing a lot of DNL, you're going to have a lot of palmitic acid. Then there's a second enzyme called ELOVE, which is an elongase. It elongates, it sticks another acetyl-CoA onto it to make it stearic acid. But then SCD1 pretty rapidly converts that stearic acid to oleic acid. So if you're doing a lot of de novo lipogenesis, what you expect to see is a lot of palmitic acid and a lot of oleic acid. And that is the reason that those two fats don't correlate with your diet, because what's more important in those cases is what your enzymes are doing. And so this is pretty much the same concept. So when you go from healthy to coronary artery disease, not only does your palmitic acid rise, but your stearic acid drops. It goes from 16.5 down to 14.4. And again, the reason for that is that SCD1, the desaturase, is desaturating all of your stearic acid and converting it to oleic acid. This is just another look at this. This is looking at the DI-18, the desaturase index, 18 length, meaning in 18 length carbons, the difference between oleic acid on top divided by stearic acid on the bottom. So in healthy people, that number is 0.52. If you have coronary artery disease, that number is 0.87. So when you have coronary artery disease, that suggests you have much more SCD1 activity, this desaturase activity. If you look at polyunsaturated fats, you can see that in healthy people, linoleic acid goes from 34.1 to 31.4 in heart disease. Linoleic acid drops if you have metabolic syndrome, if you have heart disease. Linoleic acid in your membranes drops. A lot of people jump to the immediate conclusion that means that dietary linoleic acid is good. Also, what happens is that arachidonic acid, which is an omega-6 fat, which is made from linoleic acid, goes from 14.6 in health down to 13.1 in heart disease. The pathway here is this. We have linoleic acid in our membranes. The enzymes delta-6 desaturase and delta-5 desaturase convert linoleic acid to arachidonic acid. Once they become arachidonic acid, a phospholipase, PLA2, can release the arachidonic acid from the membrane and it becomes a free-floating fat. Arachidonic acid is the favorite target of a whole bunch of enzymes that oxidize the arachidonic acid, such as cytochrome P450-1B1, which oxidizes arachidonic acid to the heats, things like 12 heat, 5 heat, 15 heat, etc. 12 heat is a fairly strong activator of something called the aryl hydrocarbon receptor, which is also implicated in the development of obesity, diabetes, heart disease. And so the aryl hydrocarbon receptor is activated by 12 heat, but it also controls the expression of PLA2 and cytochrome P450-1B1. And so you have this positive feedback loop of more 12 heat activates the AHR, which means you have more phospholipase to release the arachidonic acid from the membrane, and you have more cytochrome P450-1B1 to convert it to 12 heat. The AHR controls the expression of PPAR alpha. PPAR alpha in turn controls the expression levels of D6D and D5D. So when 12 heat is high, it activates the AHR, which activates PPAR alpha, which increases D6D, which creates more arachidonic acid, which is more likely to be cleaved by phospholipase and then converted by CYP1B1 back into 12 heat, and we repeat the cycle. When you see that in heart disease, right, remember I showed you that D6D, if you have the more active version of D6D, you're more likely to have heart disease, and that is because it's contributing to this positive feedback loop. And if you have more D6D, you're going to have more 12 heat, you're going to have more PPAR alpha. Obesity is positively associated with these heats, especially 5 and 11 in this case, but 12 heat goes from 7.5 in lean humans to 8.5 in overweight humans to 11.9 in obesity. And so all of these heat metabolites are increased in obesity. The other thing that 12 Heat does is it increases NF kappa beta. So NF kappa beta is the old school transcription factor, which controls the innate immune system, and it controls pro-inflammatory molecules like tissue necrosis factor alpha and IL-6. And so what they showed in this is that 12 Heat causes NF kappa beta to translocate into the nucleus. This is NF kappa beta in the nucleus, and it's actually bound to DNA, and it's turning on all of these other genes, such as tissue necrosis factor alpha. This is a great study. It shows the interaction between genetics and dietary linoleic acid. So this was done in Finland. People have a low linoleic acid diet at baseline, and they had them eat more linoleic acid. I think it was 30 grams a day during the study, and I think their normal amount was something like 8 grams a day. If you have the CC version of the gene, you have lower baseline 12 Heat, right? And so 12 Heat is if you eat linoleic acid and you can, and it, D5D and D6D convert it to arachidonic acid, of course, and then it's released by phospholipase, and cytochrome P451B1 oxidizes it, you have 12 Heat, right? And so if you have this genetics with low D6D activity, you have less 12 Heat. If you have TT genetics, even before the dietary trial, you'll have about twice as much 12 Heat as someone with lower D6D activity. And then in both cases, the yellow bars are they gave both groups more linoleic acid, and they converted more linoleic acid to 12 Heat. But in all cases, if you had the wrong genetics, you wind up with more 12 Heat being produced. And ultimately, all of these things, 12 Heat is activating the AHR is upregulating CYP1B1 and PPAR alpha, and all three of those things are feeding back to activate SCD1, the other desaturase. And so this really is all one big loop. And so this is that study with heart disease again, and these are healthy young men. I think they're around 30, and what you can see, and so now that we're looking at correlation with fasting serum insulin. So if you have high stearic acid levels, you're going to have, that's a negative correlation. That means you're going to have very low fasting insulin. But if you have high oleic acid levels, you're going to have high fasting insulin. You're going to be insulin resistant. This number, of course, represents SCD1 activity. So if you have, if you're making a lot of 12 Heat, you're going to have an activated AHR, you're going to have high PPAR alpha, and those are going to activate SCD1, and all of those things, of course, are going to contribute to insulin resistance by things like activating NF kappa beta. But the other thing is that stearic acid itself is a signaling molecule. Stearic acid as a signaling molecule is released as something called stearoyl ethanolamide. So if you take a rat and you make it insulin resistant, what you'll see is TNF alpha, which is an inflammatory molecule controlled by NF kappa beta, will go up by about 3-fold in expression. If you take those rats and you give them stearoyl ethanolamide, also called SEA or NSE, you can reduce the TNF alpha back to baseline because that stearoyl ethanolamide binds to NF kappa beta and it turns it off, and it breaks that feedback loop. It breaks that feedback loop of D6D leading to 12 Heat, activating NF kappa beta and activating inflammation. But if you have high stearic acid levels, that doesn't happen because you have high circulating SEA. Furthermore, if you take those rats and if you give them SEA, it lowers their insulin resistance. You can use SEA to reduce that inflammatory response that's being activated by oxidized PUFA, and you can use it to reduce insulin resistance. I sell SEA at my blog, fireinabottle.net/shop. If you get some, of course, I think that will be really good for you. You'll block inflammation. You will not have activated NF kappa beta. Tissue necrosis factor alpha is strongly associated with metabolic syndrome. Fireinabottle.net/shop. Get yourself some SEA. And so that brings us to dietary linoleic acid in this paper about heart disease. So what we saw is that in humans with heart disease, we have lower linoleic acid levels because they're being converted to the oxalams. However, within the context of having coronary artery disease. So even though people with coronary artery disease presumably have more insulin resistance and they have lower linoleic acid, within the context of having coronary artery disease and having these upregulated enzymes, if you have more linoleic acid in your membranes, it's actually correlated with high fasting insulin. So if you have high enzymatic activity of D6D, you are likely to develop coronary artery disease. Within that context, the linoleic acid is still acting as an indicator of dietary intake. That would be my argument. And so within this context, even though you have a lower linoleic acid than healthy people, if you have high linoleic acid, that means you're eating a lot of linoleic acid. And if you eat a lot of linoleic acid, you're going to have insulin resistance. If you have heart disease, you probably have elevated D6D activity. People with heart disease are the exact people who you don't want to feed linoleic acid to, I would argue. And you can see that membrane levels of linoleic acid don't really matter in the healthy people because they're not converting them to the oxalams. It's only in people with heart disease that dietary linoleic acid matters, actually, is what it looks like from this snapshot. And obviously I'm making a lot of assumptions about what these numbers mean. The story told in these two tables is extraordinarily interesting, I think. Again, my argument is that a person with heart disease is the last person that you want to feed linoleic acid to. And of course, we did randomized controlled trials of this in the 1960s and 70s when it was widely thought that polyunsaturated fats reduced cholesterol, and if you reduce cholesterol, that would reduce heart disease deaths. The Minnesota coronary experiment was a pretty large-scale study done from 1968 to 1973, and then when it was over, they never published the data because they didn't get the answer that they wanted, is really what happened. And so this guy Ramsden went and he found this decades-old data recently in the basement of the guy's house who did the original experiment, who had passed away, and showed that in fact, in the Minnesota coronary experiment, this is in women over 65, but there were actually more deaths in the women on the experimental diet where they were fed more vegetable oil. Although many would argue that this experiment, the problem with it is that these women were also getting trans fats because the dangers of trans fats weren't realized at the time. And the idea was that it was the trans fats that were the problem and not necessarily the polyunsaturated fat. But there was a study done before this one, a small pilot study called the Rose Corn Oil Trial. And we shouldn't forget about this because it is a small-scale trial. There's only 28 patients in the corn oil group, and there's 24 patients. So people were either ate their control diet, which was their diet at home with butter and whatever people used at the time, or they were given olive oil to consume, or they were given corn oil to consume. And they were supposed to eat 80 grams per day of these oils. And it says many found the treatment burdensome. Distaste, nausea, and diarrhea were the commonest complaints, so people didn't like eating 80 grams a day of corn oil or olive oil. These are the groups. This is the starting things. You can see that the people in the corn oil group were actually 6 years younger than the people with the control group, which I think will be interesting when you see the results. And this is what happened. Very simply, it was supposed to go for 3 years. But they actually ended it early because half of the people in the corn oil group were already either dead or they'd had a heart attack, or for other reasons they had to be removed from the study. And so in the control group eating butter, one person died. In the group that got olive oil, 3 people died. In the corn oil group, 5 people died. When you totaled up sudden death, and that's sudden deaths, which could be from a fatal heart attack or other reasons. If you totaled up death plus myocardial infarction, heart attack, the control group had 6 total events, 9 in the olive oil group and 12 in the corn oil group. The authors concluded the patients receiving the key treatment, corn oil, fared worse than those in the other 2 groups. 2 years from the start of treatment, infarction or death had occurred in 1/4 more of the corn oil than the control group. This difference closely approaches the conventional significance level, so it wasn't quite statistically significant, but it was very close to it. It says the probability that a true difference of the same magnitude but in the other direction may have been missed by chance is less than 1 in 1,000. So that means that the chances that the corn oil was actually good for these people and that they had somehow missed it by a statistical quirk, they say is less than 1 in 1,000. It is concluded that under the circumstances of this trial, corn oil cannot be recommended as a treatment of ischemic heart disease. It is most unlikely to be helpful, and it is possibly harmful. And so that's the one trial that I know of where humans with heart disease were given corn oil or any other linoleic acid without having any trans fats, because they were just given liquid oils, right? So there's no confoundment here by trans fats. People in the rose corn oil trial, the number of deaths were 5 to 1. So just to step back for a second and kind of think about this again. Having low linoleic acid in your tissues predicts heart disease and diabetes, because if you have low levels in your tissues, it means that you're converting those linoleic acid, you're converting that linoleic acid, you're converting that arachidonic acid. And the arachidonic acid, depending on what disease you're looking at, sometimes high arachidonic acid is good, sometimes high arachidonic acid is bad. It really depends on, that one's complicated because a lot of it is about that phospholipase A2 enzyme, that PLA2, the one that's like releasing the arachidonic acid from the tissues. But in this case, both having high linoleic acid and having high arachidonic acid were good. That predicted that you didn't have heart disease. But yet, within the context of people who had heart disease and who were converting a lot of their linoleic acid to 12-HEAT and to the other oxalams, within that context, having a lot of linoleic acid predicted insulin resistance. And that was probably an indicator of high dietary intake within that subpopulation with high D6D activity. And so that is the worst case scenario. Then you have high D6D activity along with high dietary linoleic acid, and that is going to make you one of the most insulin resistant people who have coronary artery disease. That's probably not what you want. Guys, we're going to use this as a baseline next week to talk about OXLDL. Phospholipase A2 plays a big part of that story there. So we'll go over that again. It's always good to hear about something twice. You get a better idea in your mind. Have a good week. Till then, I will see you guys next time.